As you know, light waves are basically a combination of electric and magnetic fields oscillating in time that reinforce one another uh, according to these descriptions set out by Faraday's law and Ampere's law. The integral of E dot ds is equal to negative the rate of change of magnetic flux, and the integral of B dot ds is equal to, in the absence of conduction current, is equal to mu naught times epsilon naught times the rate of change of electric flux. So a changing magnetic field produces a changing electric field, and a changing electric field produces a changing magnetic field. There's a distinct distance from the position where the electric field has its maximum value in space to the next position. If you measure down the line, that length is the wavelength. If this were a radio wave, that wavelength would be anywhere between a couple meters to several thousand meters. If this represented microwave radiation, that wavelength would be a couple of centimeters. And if this represented the highest frequency gamma radiation, that wavelength would be about the size of an atomic nucleus. Well, not only do waves vary in space and have a wavelength, but these waves, electric and magnetic fields, vary in time. In other words, there's some associated frequency as well. Omega represents angular frequency. Frequency in hertz, as opposed to angular frequency in radians per second, are related according to the formula. Angular frequency is 2 pi times standard frequency. Well, a hertz is a cycle per second, or basically a cycle means one. Now, one what? I don't know. One vibration, or one oscillation, or one complete trip, one whatever you want to call it per second. In other words, hertz are like inverse seconds. So it shouldn't surprise you that for all waves, whether they're light waves, sound waves, ocean waves, earthquake waves, the speed of a wave is nothing more than the product of its frequency and its wavelength. Let's look at the units. If frequency is in hertz, but a hertz is really 1 over seconds, and wavelength really is a separation of 2 points along an x-axis, then wavelength is measured in meters, and so when you multiply meters times per second, of course we get meters per second. So this is a generalized equation for all types of waves, and if you like it, we can put it into this triangle form. Speed is frequency times wavelength. So if you want to solve for wavelength, then you divide speed by frequency. If you want to solve for frequency, you divide speed by wavelength, and if you want to solve for speed, multiply frequency times wavelength. When it comes to light, then we replace the symbol V with C. So we can say the speed of light in a vacuum is equal to the frequency times the wavelength. The real question here is, how do we know with any certainty that the speed of light really is 3 times 10 to the 8th meters per second? That's such a large value, it's hard for me to wrap my head around any experiment that can be done to verify. For example, what if you were to stand one full football field away from your friend? So we'll say we're 100 meters apart, and you're holding a flashlight, and your friend is holding a stopwatch. So the experiment goes something like this. The flashlight's off, and you wait for the signal, and your friend yells out, "Okay, start." And then you press the button on your flashlight, and rays of light travel across the football field until your friend now sees the lights, and he yells, "Okay, stop." And he measures with the stopwatch the amount of time it took for you to turn on the flashlight and him to wait to see the light rays shine on his eyes. There's no way this is going to work. The time it takes for "okay, start" to travel from him to you is longer than the time that it takes for the light to travel. So this is thoroughly impractical and impossible to get meaningful experimental results. I'm going to encourage you on your own to do a little bit of research and look into the method by which Ole Roemer calculated the speed of light. I'll give you a hint. He was looking at, I believe, Io was the moon of Jupiter that he was observing. It dips behind Jupiter with a regular period, so there's an eclipse of Io. You just can't see it when it goes on the backside, and then it reemerges, and you can see it through the telescope. Now, Roemer lived in the generation just following the invention of the telescope, so he was one of the earliest to use these means to measure speed of light. So you predict that in a certain amount of time, you'll see Io reemerge from behind Jupiter. The problem is the light has to travel a much greater distance than just one football field. It has to travel the distance from Jupiter to Earth. And because of that large distance and the time in which Jupiter will have advanced before Io dips behind once again, Roemer was able to come up with an estimate for the speed of light. So please investigate that and see if you can see some more diagrams that indicate more clearly exactly how he came up with his measurements of distance and time. One of the best names in all of the history of physics, Armand Hippolyte Louis Fizeau. He improved upon Roemer's experimental results, and he used a rapidly spinning toothed wheel and shined a beam of light, so a light source would reflect through a partially reflecting mirror, which means 50% of the light just transmits through and doesn't go anywhere meaningful, and 50% of it reflects off and heads toward a fixed mirror over here. Now to get there, it has to fit through one of the gaps in the teeth. And so only a little pulse of light gets through, because as it rotates, then one of the teeth will block the light. So little pulses are sent down the line. Now ideally, when they reflect, the only way they can transmit back to the observer is if the next gap in the toothed wheel has shifted into position in the time it takes the pulse of light to go to the fixed mirror and back. So you can investigate further. Maybe you can see a video or an animation of exactly how Fizeau's experiment worked, but it produced a better result. But still, a better improvement was made by Albert Michelson. So in the late 1800s, right here, not far from us, in Irvine and Tustin area, you might recognize these iconic old blimp hangars that have been in Tustin for, oh gosh, almost a century now. If you look on this aerial map, there's one of the blimp hangars, and there's another one in the heart of Irvine. If you look farther to the southwest, there's UC Irvine, and somewhere in between is this street right here, Michelson. And Michelson runs mostly parallel to the 405 freeway. You've probably seen that street before. That's named in honor of Albert Michelson because he did his experiments to investigate the speed of light right there in the Irvine and Tustin area. Eventually, he moved his experiment to higher elevation where the air was clearer, and he had two mountain peaks just above Pasadena in the San Gabriel mountain range, two mountain peaks 22 miles apart, from Mount Wilson to Mount San Antonio, actually one lower peak on the perimeter of Mount San Antonio called Lookout Mountain. So he did something kind of like Fizeau. He was able to break a pulse of light up into choppy little bits by shining light onto a rotating mirror. So here's an 8-sided mirror, and let's imagine it's rotating in this direction. Then if the light hits at the moment in time that the mirror is in this orientation, that's the correct orientation to send a pulse of light traveling towards this fixed mirror. And if there's any hiking trails that'll get you there, I've never tried myself, but the pillars upon which his reflecting mirror was mounted are still there on Lookout Mountain. So the little pulse of light travels down the line. Now, all the while, this mirror is rotating. And so maybe in the time it takes for this pulse of light to travel 22 miles there and back, a total distance of 44 miles, it could be that this side has now rotated into this position, and this side of the mirror has now rotated into this position, and this side of the mirror has now rotated into this position, then that means the mirror would have advanced just right so that the angle here is enough to make this pulse of light. And it's as if the light has traveled straight down the line, and so Michelson just adjusted the angular speed of this mirror to the lowest possible value that gave the appearance that the light was traveling uninterrupted in a straight line. Knowing the distance is 22 miles, knowing the speed of his mirror, then he could figure out what the speed of light happens to be. And this is how we know that c is very nearly 3 times 10 to the 8th meters per second. So that's an interesting little piece of local history, and it turns out Albert Michelson was the first American-born scientist to win the Nobel Prize for his measurements of the speed of light.